We've got some good stuff to go over today. I'm excited to get into it. Let's begin with some announcements. Homework number 1 has already been submitted. The deadline for homework 1 was 11 a.m. today, so you've submitted that, and I think what you'd notice if you go back to Blackboard is that the submission is not visible anymore. And so my earlier suggestion last week was that you should save the PDF files locally. You should download the PDF file so you have that on your computer, so that if you want to come back to it later on, maybe as you're preparing for the exam or after the grader has provided feedback, that you have the PDF available. So save your PDFs, because homework 1 is vanished and it won't go back up again, but homework 2 is available now. That's related to cash flows, compounding, the minimum acceptable rate of return, which we'll address in class on Friday. But that assignment will be due Friday the 11th before 11 a.m. So we've got about a week and a half to work towards homework number 2. And some of the questions on today's in-class exercise are going to go towards homework number 2. I hope what you found with homework number 1 was that you were well prepared to solve those problems. As I mentioned before, it's my intention that you'll be really well prepared having gone through the in-class exercises. Those in-class exercises are meant to ease you in and gradually get you prepared for the homework, so that you don't feel confused or befuddled when you have this assignment in front of you. That was always such an uncomfortable feeling when I was a student. I want to make sure that you avoid just listening to like a 50-minute lecture that doesn't have any practical application and then suddenly having to solve homework problems that you're totally unprepared for. I don't want that to happen. So if you have questions, of course, as you're working on homework 2, I invite you to call me on Teams. I'm available during my office hours, and then also at other times outside of my office hours. So, you can always feel free to connect, and if I'm not already talking to another student or faculty member or in a meeting, then I'll definitely pick up. Okay, so any questions before we start talking about compounding? Any questions?
No.
Okay, well, then let's begin by defining some terms. We've talked about interest, but we haven't yet been explicit in differentiating between simple interest and compound interest. So let's start with the first of those, simple interest. Simple interest is a pretty rare thing that you maybe won't encounter ever in your life, maybe unless you take out a loan from your parents, because simple interest is too generous to the borrower, so to say. It's where the interest amount is only calculated on the original balance that was borrowed. So it's only calculated using the principal. And so the way that you'd calculate the amount of interest, if it's a simple interest type problem, is that you have the principal, which is the amount that was originally borrowed, and then multiply that by the number of compounding periods, and then multiply that by the interest rate per period. And so here's the formula for how you calculate the interest amount. It's far more common than simple interest to have compound interest, but let's go through an example just to show how a simple interest operates. If you have someone borrowing money for borrowing $100,000 for 3 years, and it's a simple loan with 10% per year, then what that means is that you're only going to pay interest on the original balance. You don't have to pay interest on top of interest, which is the more typical approach that goes on with compound. And so the way that you'd calculate the total repayment amount is we're just going to substitute in P is 100,000, N is 3, and then I has to be determined as a decimal, rather than, you wouldn't put in 10 for I, you'd use 0.10. So here you can see the result of that is that the interest amount would be 30,000, and so the total due will be the principal plus the interest. So this is just an illustration of how the calculations go with simple interest. And just as the name implies, it's relatively simple because you're not having to calculate the intermediate interest at the end of each compounding period like you do with compound interest. So here's our simple interest. Compound interest, on the other hand, is a little bit different because at the end of each year, the borrower asks themselves, not only how much did this person originally borrow from me, but also how much interest accumulated during the previous year. And they want to get interest on how much interest you haven't paid them yet. And so I guess the way to think about it is that you're paying interest on the original amount and all the previous interest that hasn't yet been repaid. So the formulas are going to be a little bit more complicated, but the concept is that the interest amount is the principal plus all the accrued interest. So what I mean by all the accrued interest is, if it's a 3-year loan, like we were looking at in the previous example, at the end of the 3rd year, you're wanting to collect interest not just on the 100,000, but on how much interest compounded during the 1st year, during the 2nd year. And so all of the previous periods are considered in addition to the period in question. By the way, I notice that a few people are just now joining the lecture. It's really important for you to be on time. If you miss the announcements, then you're missing out on some really important details. And so I'll encourage you to make the effort to join the lecture on time, because I don't want anybody to become confused or miss a deadline because they joined the class late. So please do your best to join before 11 o'clock. All right, so here's the formula for how you would calculate the interest just during a certain period. So here T is referring to time period. And so the interest amount in, for example, the 3rd year. If you're going to find out the interest amount if T equals 3, so we're talking about in the 3rd year, then it depends on the principal that was borrowed, and then this summation is saying it's the interest quantity from all the previous periods. So it would be the interest amount that accumulated in the 1st year, the interest amount that accumulated in the 2nd year, and then you add that to the principal, and then you can see with these parentheses that the interest rate is applied to all of what's inside those brackets. And so the interest applies to all of it. So let's look at an illustration. That same $100,000 quantity, if it's being borrowed for 3 years and the same 10% interest, but now instead of just simple interest where there's no compounding, now we're saying that the interest does compound annually. So let's take this step by step.
Can you go back to the equation?
Yep. So just while I've got that on screen, presumably you're copying it into your notes, and that's great. The thing I'll mention about this is this isn't calculating the total interest for the entire loan. This is I sub t is just talking about the interest that's due in a certain period. Kirsten, have you got that?
Yeah, thank you.
Sure. All right. So here's what's going on in the 1st year. In the 1st year, you borrowed 100,000, and so 10,000 is how much interest accumulates during year 1. So think about at the end of the 1st year, how much do you owe? Well, you owe the amount that you owed at the beginning of the 1st year, because it's at the beginning of the 1st year that you receive the 100,000. So as soon as you get it, you now owe 100,000. But at the end of the 1st year, you owe the 100,000 and all of the interest accumulated during that period. So it's 110,000 that you owe after 1 year. At the end of the 2nd year, you're going to owe more, and the interest is actually going to be higher during the 2nd year, because now you owe 10% not just of the principal, but you owe 10% of the total balance that existed at the end of the 1st year. So the interest amount, instead of 10,000, now it's 11,000, because you're paying 10% of the total balance at the end of the first year. And then the same pattern continues at the end of year 3. At the end of year 3, you're going to owe the previous balance of $121,000 plus 10% of that previous balance. So 10% of the previous balance is $12,100. And so the total that you owe at the end of the third year, assuming that you haven't made any interest payments or principal repayment in the intervening years, so this has just all been accumulating with you haven't been paying your debt yet. So for compound interest, you owe $133,100. So now you can see why banks and lenders generally prefer compound interest rather than simple interest, is because they get more back. In the case of simple interest, the amount that was going to be paid was just $130,000, but now it's $133,100 if it's compounded annually. So the $3,100 difference, that represents the interest on top of interest. So if the interest rates are high enough and the time periods are long enough, this can really be an insidious effect where you're having to pay quite an enormous amount because of compounding interest. And that's why, for example, credit card companies like to compound monthly, is it helps to improve their revenues since they're receiving interest on top of interest. So just again, here's the formula that we use to calculate the interest amount in any particular year. So the interest amount in any particular year is the principal of $100,000, and then all of the previous year's interest is multiplied by the 10%. So for example, in the third year, 121 was the 100,000 principal plus the 10,000 interest from year 1 and the 11,000 interest in year 2. And then all of that was multiplied by 10,000. So we can do compound interest calculations like this using a spreadsheet. And we're going to use spreadsheets a lot this semester. By the way, I think that I've probably rearranged the slides just a little bit compared to what you may have printed out. And I hope that doesn't throw anybody off. There's no reason to be concerned if you do notice that I've rearranged things. You can just put an arrow at when it fit into the lecture. But just occasionally I decide that I want to talk about one thing before another thing. So that's why the slides are a little bit rearranged compared to the ones that are posted online and available for you to print out. So here's, I think, probably what was showing first if you have the printed notes. So this is the example that we solved during our in-class exercise with Monday's class. So hopefully this looks familiar. This was the fourth problem in the in-class exercise number 4. And what we did in this in-class exercise is we took a look at 2 different ways to solve it. The first way was, I told you, with these bullet points, take each of the amounts as though it's an individual present value that's compounding into the future. And so, for example, what you did was you said 12,500 multiplied by 1.05, because I, in this example, was 5%, and then you used n equals 3 to get the amount from year 1 to year 4. So we were shifting the time. In accounting for the time value of money, what we were doing is we were moving this arrow to year 4. And so when we were moving the arrow at year 2 to year 4, then n was only 2 for that one. And then we moved this individual present value, that's how we were treating it, we moved it 1 year to get to year 4. And so we found the total equivalent future value just by moving the individual present values into the future. We treated the annual series as though it wasn't really an annual series. We treated each one of those arrows as though they were individual amounts. So that's the first way we solved it. And the other was I showed you this handy formula. It was a ratio, the ratio of the future amount to the annual series, so that if we rearrange the ratio and move the a to the right-hand side of the equation, then we could solve for f directly. And so that was a quicker way to do it. There's even a third way, though, to solve this example. Using the approach that we've been talking about so far in today's lecture, what we could do to solve this example is we could create a table. And we could set up a table where we're looking at how much have we taken and how much are we going to owe at the end of each time period. So if you look at what I've set up for the columns in this table, we have the amount that we've taken as the loan, the previous balance that had accumulated, how much is subject to 5% interest, the interest due at the end of the period because of how much we cumulatively owe, and then the new cumulative balance. And so let's look at year 0. We didn't get any money yet at time 0, so we don't owe anything. But at the end of the first period, the cumulative amount owed is going to be $13,125. And what we do is we go through the end of the second period. You've now taken $12,500 and the previous year's balance at the end of that period. And so you can see it's a sequential year-by-year accumulation, and we get the same $53,877, and that was the answer when we solved it. Either of these other methods gave us the same $53,877. I just wanted to show you that we can progressively step through time and also identify how much is owed by looking at how much interest accumulates in each period. And so this approach that's shown in the table here, basically what we've done is used this formula in order to calculate the interest amount in this table. And so the interest just keeps piling up, and you can see how we step through that. So this is just an illustration, maybe a preview of things to happen in the future. We will set up Microsoft Excel spreadsheets, and you're going to learn how to do the same thing. And you know, one of the advantages of us doing this remotely is if you have 2 screens, then you'll be able to on one of your screens show the demonstration I'm doing, and then on the other screen you can solve with Microsoft Excel. So you know, even if you're watching the lecture on just your phone or an iPad, or if you could bring it up on a TV by plugging an HDMI cable into your laptop and having 2 screens. But the point is, there will come a point where we're doing demonstrations with Excel, and it'll be useful if you can see what I'm doing, and then you'll have Microsoft Excel up also on your own computer. So this is a preview for now. All right, some other concepts that we need to introduce are the difference between nominal interest and effective interest. And the difference between these two different types of interest is that nominal interest doesn't account for compounding, where effective interest does account for the effect of compounding. That's the effect that they're talking about, is compounding during a year. So nominal interest is where the interest maybe is being compounded on more than an annual basis, but it's just quoted on an annual basis. So for example, if it's 16% annual interest, but it's compounded quarterly, then it's not really 16% interest, because it's going to end up, the effect of paying interest on top of interest is going to make it so that on a percentage basis it turns out to be more than 16%. And so what you need to do is divide the nominal interest that's quoted by the number of periods per year. And so here, if it's compounded quarterly, that means that there are 4 compounding periods in a year. And so really what the interest is 4% per period. So 4% per period, if there are 4 periods per year, is only nominally 16% per year. So another way to think of the word nominal is not really. because that's not really the interest that you end up paying. If it's compounding more than once per year, then it's the effective rate that's going to apply. So if you have 4% interest per period, then the effective annual interest rate is going to be greater than 16%. And let me show you here on the next slide the formula that will allow you to calculate the effective interest rate. But the place where this comes into play most often is with credit cards. So a credit card maybe says that it has a 24% nominal interest, but the effective rate will be much higher because a credit card would compound monthly. So here's the formula that allows you to calculate what is the effective interest rate based on the nominal interest rate. So here you can see that the terms being defined is R is the nominal interest rate per year, and then M is the number of compounding periods per year. So in our previous example, if it's 16% per year, then what we would do is we would have 0.16 for R, and then M would be 4. If the interest is compounding quarterly, then that means that there are 4 quarters in a year, so M is 4. So we could find out what's the true effective interest rate for this nominal rate of 16%. And I don't think I have that on the next slide. Let me show you. I have some hand calculations, I think. Yeah. So here's how we could calculate. Okay, so this example of 16%. All right, well, let me just make it full screen. It's nice and big this way. Okay, here's the formula for I effective. We want to find the effective annual interest rate based on the nominal that's given. And so if the nominal is 0.16 and M, the number of compounding periods per year, is 4, then what we're essentially doing is 1.04 to the 4th power, and then here you can see at the end of the equation is -1. So if the nominal interest rate is 16% per year, then on an effective basis, then that means that really what you're paying is 16.986% per year. So just in conclusion, what I'll say is you can either pay 4% per quarter and then have it compound every quarter, or you can pay 16.986% per year with annual compounding, and then it would be the same. So this nominal versus effective is all about how often the compounding occurs. And sometimes compounding occurs at more often than an annual rate, but it's still customary to describe interest on an annual basis. Okay, in the in-class exercise that we're going to work through today, we're going to refer to this ratio of F to P. So we've seen it before. It's the ratio of the future amount to the present amount, and so if you want to calculate the future amount, you just move the P to the right-hand side of the equation, and I think I even include that on the in-class exercise paper. Yeah, here it is on the first problem. So hopefully you have printed these out by now. I've been telling you for several days now that you ought to print out the in-class exercise papers. Those are available on Blackboard if you still haven't done it yet. But let's work through the first 2 problems using the formula that's provided there. I'll pause for a moment to give you some time to calculate this, and of course, as we always do, after a few minutes for you to work on this, and you're welcome to type your guesses into the chat box if you choose, then I'll come back with my solution, and that allows us to double check that we all got the same numbers and that you were headed in the right track. All right, so we already had somebody weigh in with the correct answer for number 1. Christopher verified it. Good. Let me pull the solution over here on the screen for the first two. Okay, so this is a ratio. F to P is 1 plus I to the N. Okay, so if we calculate this number, the 6.6143, what that number means is it's the ratio of the future amount to the present amount. So if the present amount that you deposited was $25,000, then what that means is after 30 years you have 6.6 times as much money in the account as you initially deposited. So that kind of shows the power of compounding right there. If you're willing to be patient and allow the money to accumulate for a lot of years, then your earnings really accelerate the longer you leave it in. And as I'll address when we talk about our project, that's also a reason why it's so valuable for you to begin saving money for retirement when you're young. And it may seem counterintuitive to be saving for money that you won't spend until you're in your 70s when you first start your career in your 20s. But if you deposit $1 into a retirement account when you're very young, then that dollar is earning interest for so many years, and then the interest that it earns compounds. And so you can have exponentially, literally exponentially growing retirement account if you save really early. So here, I just expressed it as a ratio to make the point that compounding is powerful. So the future amount, $165,359.15. So, of course, since we're doing this in our calculator, we can be accurate to the nearest penny. If we were looking up this factor out of the back of the book, because that factor, well, maybe not for the 6.5%, but the back of our book has these ratios for like 3% interest, 4%, 5%. It wouldn't probably have an odd number like 6.5%, but later on we'll be able to look up these ratios. And so here when I say 6.6143, there are additional digits beyond that potentially as well. It may continue. And so I don't round off in any intermediate steps. You round off at the very end so that your calculations are accurate to the nearest penny. Okay, now similar thing for problem 2. We're given the F, but you're solving for the P. So we can still use the same formula. We can use that the ratio of F to P is 1 plus I to the N power. But now, instead of solving for F like we did in the first problem, this time we're solving for P. So just rearranging algebraically. Now you can see here, I say that the ratio is 1.8009, and then I have the dot, 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 that ellipsis, as it's called. The dot, 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 dot just means that like there's more digits of precision that I've left in the calculator. I haven't rounded it off. And then at the very end, we round it to the nearest penny. So there's a question, say your answer was a certain number of dollars and then less than a penny. You only round once. Yes, that's right, at the very end. And so if it's less than a penny, then it rounds down and that additional amount isn't seen. So yes. Any questions about either of these first two questions on the in-class exercise? So you can see the effect of compounding there. In the first one, you deposit $25,000 and you could withdraw $165,000. And the reason why that's possible is because interest is being earned on top of the interest. And the same thing is true in problem 2. If you need to be able to withdraw $95,000 because maybe you're saving for someone's college retirement, you don't have to deposit as much money as you're going to withdraw, because in the intervening years, the interest is accumulating and compounding. All right, now this is a question that has to do with the difference between nominal and effective interest. So just as a refresher, let me get the formula for that. Here's the formula for nominal versus effective. I may even be able to paste it on here. There, okay. So what I'd like you to do is try and decide which one is better. Well, I guess there's a couple of different ways to solve this one. Maybe for now, let's not use the nominal versus effective interest formula. Now that I think about it, let's do this. 7.5% compounded annually means that I is 0.075, and then if it's going to be for 10 years, then that means n equals 10 for plan 1. But plan 2, since it compounds monthly, then what that means is that there's going to be 120 periods, so n equals 120, but now I will be this interest rate divided by 12. So we're actually still going to use the, if we're calculating for F, because we're depositing P, so we can use this ratio, but the I and the N are going to be adjusted depending on how often the interest is compounded. So what I'd like you to do is find out how much money do you get if you go with plan 1, and how much money do you get if you go with plan 2. So deposit $125,000 into both of those accounts, and then find out how much extra money would you get by choosing the better of those two options. So you need to calculate the future amount with both plans. Plan 1, I equals 0.075 and n equals 10. Plan 2, I is this divided by 12. Now it's going to be as a decimal, so it's 0.0725 divided by 12. That's the I, and then n is 120 because there's 120 months in 10 years. All right, let me bring up the solution for this third problem onto the screen, and we'll look at the difference between the two plans. Okay. So you can either take plan 1 or plan 2. Plan 1 offers annual compounding, and you'll notice it has a higher interest rate, 7.5%. So the question is it better to have the higher interest rate or to have the plan that compounds more often? You know, maybe whoever's offering plan 2, maybe they would brag and say, well, maybe we offer the lower interest rate, but we compound monthly. So, you know, monthly compounding is better than annual compounding, so you should accept the lower interest rate. So we need to figure out, you know, which one is better. So if you go with plan 1, then the ratio of the future amount to the present amount. And so going back to this formula, the ratio of future to present is 2.06103. So if we multiply that ratio by the present amount, that gives us the future value will be 257,628. Now plan 2 is different because it has the monthly compounding, then that means there's 120 compounding periods, and the interest rate per period is only going to be 0.00604 and so on. So that 1 plus I to the n power is going to give us a different factor that's slightly lower than plan 1 was, and so that means that we would only have 257,529 for the amount you could withdraw from plan 2. So plan 1 is better. you will earn an extra $99.92 if you go with Plan 1 instead of Plan 2. So this is the first time where we've solved a problem that had compounding that was more frequent than annual. So the annual interest, you're expressing the interest on an annual basis, but it compounds monthly, and so you need to figure out the interest rate per period. So per period is a really important component of this, differentiating between annual interest and interest rate per period. Okay, so let's look now at the next problem on the in-class exercise. Now this is where we're going to, I was premature before, this is where we're going to use the formula to calculate the difference between nominal and effective interest. So here, the nominal rate is 24% per year, and we want to find out what's the effective rate if it compounds quarterly. So that means that there are 4 compounding periods per year. So m equals 4 for this one. M equals 12 for monthly. And m equals 365 if the interest is compounding daily. So R is 0.24 in the formula. So R is going to stay 0.24 because R represents the nominal interest rate, and what we want to find out is the effective interest rate for a variety of different compounding frequencies. The solution up on the screen so you can see it. Okay, so quarterly compounding means that there are 4 periods per year, and you can see that 24% nominal turns into 26% effective if it's compounded quarterly. Oh, I have a typo here, don't I? Because that should say 12, but I think that my number is right even though I have a typo. Did somebody else get 26.82? Yeah. So let me change that now so that that typo doesn't get me next year. So that's 12 to the 12th power. Okay. And then 0.24, so 24% nominal turns into 27.11 effective if it compounds daily. So you can see that it's diminishing returns. You know, if we compounded hourly, that wouldn't get us very much difference for the effective interest rate compared to daily compounding. It's reaching an asymptote of the effective interest rate is approaching a maximum value. There is such a thing called continuous compounding. I guess that would mean it's compounding every second, but it reaches some maximum value. But what you can see is that, of course, the credit card companies have an incentive to compound your interest more often than annually because it ends up in them receiving a better return. All right, with the 2 minutes that remain, let's just, oh boy, we have 2 problems. We may not get to both of them. We have translate the following into a cash flow diagram. So just putting a sketch together there. And then practicing the A to P ratio. If you're going to loan someone $27,000 and they're going to give you annual payments, what is the amount of the annual payment? Calvin asks, should we round to a certain decimal? For the interest rates, I don't think there's a hard and fast rule. You know, like if you do it to the nearest hundredth of a percent, that's probably going to be accurate enough. All right. So, all right. So I regret that we're going to have to rush through these last 2, but let me just demonstrate it for you so that we see the translation of the cash flow diagram. Let's just make sure that all of the elements are here. Okay, so your uncle is going to get a revenue of $247,000 each year. So that's a known amount. So it's a solid line. Each one of the arrows is the same length because it's an annual series. We know that the interest rate is 4%. Does it say that in your problem statement? Yeah, interest rate of 4%. So we just put that somewhere on the cash flow diagram. There's going to be fuel costs of $4,500 per year, so smaller arrows going down. There's the single refurbishing cost for the overhaul at the end of the third year. So here you can see the $55,000 for that F value. And then there's a single salvage value because the truck is going to be sold at the end of the 5 years for $95,000. And so what we're trying to figure out is how much can you afford, let's see. In the problem statement here, does it say, oh, how much can your uncle afford to spend? Yeah, so the unknown is in the present, how much should you spend in order to buy this truck and have those revenues and expenses coming to you? All right, we're out of time. We're going to come back and take a look at the last problem on that in-class exercise in our lecture on Friday. That's all I have for you today. Just remember that you can get started on homework 2. It's available now. So the early bird gets the worm on that. Hope you have a great day. I'll see you on Friday.